record and share the screen. Okay, so let's do some of the problems as suggested by you guys in the last class. We'll do some of the problems from the chapter capacitance, right? These are some of the past paper problems. We can also do, so whatever topics that we have covered so far, electric fields and the other ones as well, we can do these questions, past paper questions from those topics as well, right? So you can let me know. Let's keep one session on perhaps a Saturday where we solve the past paper questions from the chapters that we have been doing. You're giving your exams in October, November, right? All right. So, okay, there are some for May, June. Okay. All right. All right. So if they're giving in May, June, if everyone is giving in May, June, then we have time to do past paper questions as well. All right. So let's start with this one, capacitance, right? So I'm going to see that if I can keep your chat opened, and let me just, because I'd still prefer if you speak. So we're going to do it in this way that you're going to help me solve the problem. So it's I would recommend to unmute yourself and let's work out these problems together, right? So let me go to full screen. All right, so here we have question number 1. We have a solid metal sphere of radius r, and it's insulated from its surroundings. The sphere has a charge q on its surface. This charge is on the surface of the sphere, but it may be considered to be a point charge at its center. All right, so first of all, they're asking to define capacitance, right? And that's pretty straightforward, because if you remember this equation for capacitance, we have this equation that charge is the product of capacitance and voltage. So this equation defines capacitance for you as the ratio of charge, what do you call this word? Allotted, I guess, on the surface of the conductor to its potential difference across the plates, right? So you can define it as a ratio of charge to the potential difference. Right? So that was pretty straightforward. Next is show that the capacitance C of the sphere is given by this expression. So that's also pretty straightforward, because if you remember from your AS, we define the potential difference on the sphere, right? If this is a sphere of radius r, then the potential difference is given by charge q that is on the surface of the sphere divided by 4 pi epsilon naught r, right? Where r is the radius of this sphere. So then we'll just use this equation, q is equal to c times v, which gives me c as q over v. But v is what? This thing. So I put that q over 4 pi epsilon naught r, right? And the charges cancel out, and this thing just becomes this thing will go upstairs, and this will become 4 pi epsilon naught r, right? And that's the capacitance that we had to show. So it's clear? No problems? All right, so the next part says that the sphere has a radius 36 centimeters. Determine for this sphere the capacitance, right? So that's also, again, pretty straightforward. The radius is 36 centimeters. Just remember to convert it into the SI units, which is meters. So it would be 0.36 meters, right? And then use this equation for capacitance to write that down as 4 times pi epsilon naught times the radius, which is 0.36 meters. right? Epsilon naught is, this had the value, if you remember, 8.85 into 10 raised to power minus 12, right? And then you just do the math, and this gives you a capacitance of 4.0 into 10 raised to power minus 11 farads, right? So you have to write it in terms of farads. So you'll just use this thing. So 4.0 into 10 raised to power minus 11. Any questions from anyone so far? Clear. Okay, so let's move on to the next part. Okay, so now they're saying find the charge required to raise the potential of the sphere from 0 to this many voltage. So we have to find the charge that I have to provide to the sphere. If you remember from our lecture, we saw that if I keep supplying the charge, it increases the energy that the capacitor can store, which means basically the potential difference across the capacitor increases, right? And so we can just find this charge store by Q is equal to C times V. Now, if we want to raise the potential from 0 to 7 point this one, right? So we can just use this expression. If you remember, we saw that we can write this as VF minus VI. Clearly, VI is just 0 because we're raising it from 0. So this reduces again to C V, and we can just use the subscript F for the final voltage. And capacitance, as we computed just now, was 4.0 into 10 raised to power minus 11 farads. And then multiply this with the potential difference across the plates. That's 7.0 into 10 raised to power 5 volts, right? And now you just simply do the math, and this gives you 2.0, 2.8, because 4 times 7, right? And into 10 raised to power, so minus 11 from here, 5 from here. So this would give you minus 5 coulombs, right? So the charge is 2.8 into 10 raised to power minus 5. All right, hopefully no questions up to this point as well. Is it clear for everyone? All right, so okay, now suggest why your calculations in part B, right? Whatever we just did, we found the charge store in part B, and we found the capacitance of the capacitor, right? So they're saying that suggest why these calculations for a metal sphere would not apply to a plastic sphere. Any ideas, any suggestion that you would like to say? Why are these results, the equations that we used? Yeah, so plastic is an insulator. So what happens on an insulator? Why is it really so why can we not store charges on an insulator? Because I mean, of course, it's a 3 marks question. So yeah, so basically you'll say that plastic is an insulator, right? And on an insulator, you do not have any free electrons that can move, right? And if electrons are not allowed to move, that means charges are not allowed to move. And so you charge, how will we store charges if they cannot move, right? So is an insulator which has no free electrons. I hope the concept of free electrons is clear to everyone, right? So if there are no free electrons, charges are stationary, right? And if the charges are stationary, then you cannot store them, so they'll not move across. So there will be no single value for the potential difference across the plates, right? So is that clear? So this thing just really means that the potential difference will not have a unique value. It's just implying the fact that you cannot really store the charge at the center of the sphere, as we started the problem off with, right? We were saying that the charge is considered to be at the center of this sphere, right? All right. So the next part, we have a spark suddenly connects the metal sphere in part B, the one that we have been dealing with. Why is this for 3 marks? Right. So the first mark basically you're getting for is specifying that what plastic has no free electrons, right? So you're just telling them that plastic is an insulator which does not have any free electrons, basically, right? And that gives you a 1 mark. The second mark is coming from the fact that you have to elaborate on this fact that what do you mean by it has no free electrons, which it just means that the charges are not allowed to move, right? So if they're not allowed to move, that means that charges are stationary. And the final mark is just coming from the fact that you are basically implying this thing that you cannot store charge at the center in this way of a plastic, right? You cannot do that because it's, again, there are no free electrons. Is that clear, Hasi? All right. So coming back to this one, that a spark suddenly connects the metal sphere in part B to the earth. So basically, you're earthing this metallic sphere, causing the potential of the sphere to be reduced from 7 whatever is this to 2.5 into 10 raised to power 5 this thing, right? So clearly what's happening is that the potential is being dropped, right? So in the problem we see that the potential is being dropped. So if the potential is being dropped, then clearly, as we saw from the lecture, you immediately know what would happen in terms of energy. Energy should also drop, right? And that drop in energy is what they're calling the energy dissipated in the spark, because the spark is responsible, or the energy loss, the spark is responsible for this energy loss, right? So this the energy lost from this thing was the energy gained by the spark. So the spark could have happened in the first place, right? So we just have to simply compute this energy, and we can easily do that by remembering that this energy is just the work done, right? And this is equal to half CV squared. Now, of course, we have a range of potential, right? It's dropping from a specific value to another certain value. So we can rewrite this expression as half C times VF squared minus VI squared, right? Something like this. And this would just give you half. And the capacitance, it is the same sphere, right? Because they're saying that it's the same sphere in part B. So the capacitance for that particular sphere was what? 4 into 10 raised to power. No, that was the charge. Let me just quickly go back and check. What was the capacitance? Yeah, it was 4 into 10 raised to power minus 11, right? That's what we computed. So 4.0 into 10 raised to power minus 11 farads times the difference in these voltages. So the final voltage is a drop, right? So we have this thing 2.5 into 10 raised to power 5 minus 7.0. This is squared, right? This value is squared minus 7.0 to 10 raised to power 5. And then this thing is squared as well, and wall squared. And we have farads from here. All right, now this is clearly going to give you a negative solution, right? Because you see that you have a lower value minus the minus a higher value, and so this gives you minus 8.6, approximately minus 8.6 joules. But the answer that I'll write over here will not include that negative signature. Can you tell me why? Can anyone tell me why the answer will not have this negative sign? Energy is scalar. I mean, well, okay, but you can still say that the negative sign is showing me that the energy is being lost, right? The energy is being removed from the system. You can say that, right? Energy is a scalar, but the negative sign is at least telling you that the energy is being removed from the system. Nothing about the direction, but the fact that the energy is being removed from the system. But in the problem statement, they're saying calculate the energy dissipated in the spark, as in calculate the energy removed. So initially they're specifying that the energy is being removed. So you just write the magnitude of this answer, which would be 8.6 joules, as in 8.6 joules of energy has been removed from the system to the spark, and the spark gained this energy, 8.6 joules, right? So that's clear. All right, so let's move on. Okay, so we have another problem that says we have to state two functions of capacitor in electrical circuits. So any idea? So you have to just tell the two functions of a capacitor in an electrical circuit. The first one should be very obvious because it comes from the definition of the capacitance or a capacitor itself, which is that it stores energy. So in this case, you can, if I write stores energy, that implies that it stores a charge as well, right? So as in, like, it's the same thing kind of as storing charge. You cannot say the next function is storing charge. That is the same thing as storing energy, right? What could be another function of a capacitor in an electrical circuit? So this thing you should think about it by whatever the theory that you studied about capacitors, apply it to a practical application, as in a circuit, right? And any electrical circuit. Any idea? Okay, so you can say that it is the cause of electrical oscillations, right? Why do I say that? Can anyone put light onto that? Electrical oscillations, as in, like, it would make the circuit behave, you can say that it would basically block a direct current. It would look like an alternating current, right? So that it's like electrical oscillations. Because okay, so basically when you connect it to a circuit, it's continuously taking a charge from so the battery supplying the charge, it's the charge is being removed from the plate. It will just block the direct current. Any more direct current will be blocked, and I'll tell you why. Because if you remember how capacitor worked, the charge was the battery was supplying it the charge, right? And the charge was not stationary as in the charge was continuously changing. So I attach the battery to the capacitor. So let me just try to draw it. And we saw that because the electrons will flow from this to this thing, so there will be some excess electrons over here and some excess positive charges over here, which is just the absence of electrons, right? And so this thing is continuously happening. So it behaves like an oscillation, right? So it's charge is coming, going, charge is coming and going, and charge is coming and going. And so it behaves like something like this, right? So basically it is producing electrical oscillations in a circuit. So does that make sense? All right. So the next part is that you have three capacitors, each marked 30 microfarads, right? So let's just mark that. Why is it not writing? Can you see? Is it writing anything on the screen for you? Yeah, now it's working. All right. So let's mark it as 30 microfarads, 30 microfarads. And they can the plates of the capacitors can have a maximum potential difference across them of 6 volts, right? That's what the question is specifying. They're arranged in this arrangement, so we have a combination of series and a parallel arrangement. Determine for the arrangement shown in this figure the total capacitance, as in the equivalent capacitance, right? And that's, again, it's pretty straightforward if you remember. First of all, let's simplify this circuit so that it looks like this, right? So basically, this capacitor is the equivalent of these two parallel arrangements, right? So this one is 30 microfarads initially. This is my point A, and this is point B. Simplifying a parallel capacitor circuit, we just add the capacitance together, right? So it would just be, let's call this this thing, let's call it CAB. I'm just going to call it CAB, right? So this would become 30 plus 30, right? So this 30 plus this 30. So 30 microfarads plus 30 microfarads, and that's 60 microfarads. So the capacitance coming from the parallel combination of the capacitor is 60 microfarads, and that gives you your 1 mark. The second mark is coming from the fact that, of course, you compute the total capacitance. So now the CAB, actually, let me just keep it as CAB is equal to 60 microfarads. And now the final arrangement is a sequential or a series arrangement of these two capacitors. So all you have to do now is just add these two capacitors in series, which would be or I can just write it as 1 over 30 microfarads plus 1 over 60 microfarads, and then take the inverse of this thing, right? And if you take this LCM and then you take the inverse of this, so this becomes 20 microfarads, right? So that's the equivalent capacitance of this circuit. Hopefully that was pretty straightforward as well. Any questions from this part of the problem? Clear. All right. So now the next thing is that the find the maximum potential difference that can be safely applied between points A and B, right? So each capacitance can safely have a maximum of 6-volt potential difference across their plates. So meaning you can only, so if I supply any charge that would cause the potential difference to be greater than the 6 volts, then the capacitor will what do you call it, break or become faulty. It will no longer work, right? So we have to be careful so that the potential difference does not exceed 6 volts. Now, using these capacitors, each that can have a maximum of 6 volts across them, we want to figure out the potential difference that is safe for the entire circuit made up of these capacitors, right? So what would that be? Any idea? Any suggestion? Not really. Okay. So if I look at this thing, there we have 6 volts maximum for each, right? Now we know that the potential difference in parallel stays the same, right? And so this means that the potential difference across the parallel combination will be just half the potential difference across a single capacitor, right? Because in parallel we have these two what do you call these things, capacitors, right? And so the across a single capacitor we have 6 volts. So this should be 1/2 times 6 volts. So this is across the parallel, right? Only the parallel. So let me just write it as this parallel. Let's say across parallel. So it would be 6 volts divided by 2, which would be 3 volts, right? And from series, so in this the remaining is this 6 volts coming from this first capacitor, right? So that is you can so the total would be this 3 volts coming from here plus the 6 volts coming from the first capacitor, right? And this would make a total of 9 volts. So that's the safest potential difference that can be applied across these two endpoints A and B. So does that make sense? Is that clear? All right. Okay. So is everyone following along? All right. So C part, a capacitor of capacitance 4700 microfarads is charged to a potential difference of 18 volts. All right. So it is then partially discharged through a resistor. So we saw that we can discharge capacitors as well, and we can so one of the ways to do that is by attaching a resistor to our circuit. The potential difference is reduced to 12 volts. Calculate the energy dissipated in the resistor during the discharge, right? So if the resistor is responsible now for the discharge, as in previously you saw in the previous question, we saw that a spark was responsible for the discharge of the capacitor, right? We earthed it, so it was discharging, and that spark was responsible. In this case, we attached, so the problem is exactly the same as before. In this case, we just attached a resistor to this circuit that contains a capacitor of 4700 microfarads, and we want to find out what would be the energy lost to that resistor so that the potential difference decreases, right? And again, that would be very straightforward because we know that that energy that is lost is just the work done across the plates of the capacitor, which is half CV squared, right? And again, the potential is dropped from one value to another, and these are both two positive values. So I can write this as half C VF squared minus VI squared, right? And this gives you half into capacitance is 4700 microfarads. So remember to write the prefix as well as into 10 raised to power minus 6 farads, and then you just use this thing. So it's reduced to 12 volts. So 12 volts minus 18 volts, but you have to square these as well, right? So once you do this math, this gives you the energy as negative 0.42 joules. But when I write it over here, I'll write the absolute value of this thing. Again, the reason is because they're saying the energy dissipated in the resistor. So they're already specifying that the energy is lost, right? So that energy is 0.42 joules. Is it important to write F and V? Okay, so I always recommend that write down the units while you're performing, while you're doing the working as well, right? And the reason for that is if you're doing so, you tend not to make a mistake when you're writing the final answer, right? So you don't know, maybe they're asking you what in whatever units they're asking you the final answer. If you write the units, then it helps you to keep track of them, basically. So that's why I recommend to write down the units as well. It helps you in understanding what units will cancel. And sometimes if you forget an equation, for example, then if you know the units of the equation, then it helps you to retrace that equation as well, right? So that's the only reason. Okay, so all right, so now let's move to the next problem. We have a graph, but before that, we have this thing, two problems. State that what is meant by electrical potential at a point. So that's pretty, sir, can you show that question again from the start? I lost connection between. All right, so you mean the state, which one, which part of it? Can you specify the part? I mean the part A where you specify two functions of the capacitors in circuit. That's probably clear, right? BI. Okay, so this one. So do you want me to go over it again as well? All right, okay, I'll quickly do it. So in the I part, we have the circuit. We have two capacitors and connected in parallel, and one in series with those two parallel capacitors. Each have a capacitance of 30 microfarads, and the safe potential difference across the plates is 6 volts. If I applied more charge, then it would give. So I supply the charge, it increases the potential difference, right? If I supply more charge so that the potential difference increases, then 6 volts, then the capacitor breaks down. So we don't want that. Now they're saying that determine for this arrangement the total capacitance. So we first figure out the capacitance of this parallel arrangement, right? So that we can redraw the circuit in this way, while this capacitance, the second one, I called it CAB, is just, actually I should have not called it CAB, but I did it anyway. It doesn't matter. It's still the equivalent of this parallel combination, right? This one. So I'll actually even highlight this thing, and I'll say that this is this one. All right, now it makes it clear. So so we just use the sum of the capacitors, because in parallel the capacitance is the sum of those two capacitors. So 30 plus 30 is 60 microfarads, right? So then that means this capacitance, that sum of these two, would be 60 microfarads. Now that's where we get the 60 from, but we want to find the total equivalent capacitance. So this one is in series with that. So we just add this one plus this one, whose capacitance was 60 microfarads in series, right? So in series, we know we add capacitance in this way. So when we do that, this gives me 20 microfarads, and that's the equivalent capacitance, right? So that's clear, Hasib? Or do you want me to continue the second part as well, or was that the only first part?